All right, so let's get started. And as you already know, today we're going to talk about how to build a machine learning, a workflow, a monitoring workflow for machine learning systems that are running already in production. And we're going to start with a kind of overview and a very high level. Maybe we're going to go to middle level at some point, description of how to do it. And then William's going to give a demo of how it actually works on a real world data set. So let's get started with the agenda. We're going to first walk through the three main parts of the machine learning monitoring workflow, which is the performance monitoring, the root cause analysis, and the issue resolution, which kind of, makes sense. You first identify whether there is an issue with performance monitoring, then you find out what are the actual causes for the issue, and then you resolve it. And then we're going to have a session with William where he will, in like hands-on fashion, show how to actually do it step by step. So in terms of the monitoring flow, as you already know, it consists of 3 steps. The first one is performance monitoring, and this is the only step that you need to do constantly, kind of in like online or mini batch fashion, when you will constantly monitor the performance of your machine learning models. And if you see that there is a drop, then you will enter the second stage, which is the root cause analysis, which is ideally fully automated, but at least it's augmented, so you don't have to do all the work yourself, and most of the work is done by an automated system. And then the last step is issue resolution, when you resolve the issue, and then you will double check again with performance monitoring whether issue has been successfully resolved. So why do we need machine learning monitoring? The goals are threefold. First, we want to maintain the business impact of the model. The model, when it is deployed to production, is supposed to fulfill some kind of business goal. And this business goal is only fulfilled if a machine learning model actually makes predictions with the quality that is expected of it. So if performance degrades, then business impact will also degrade, and it might actually start doing more harm than good. The second thing is reducing the risk of the model. All machine learning models that are deployed to production operate in at least semi-autonomous fashion in the real world, which means that they impose additional risk on the organization, and it is something that we want to reduce and ideally eliminate by having full observability of the actual model and everything that comes into it and out of it. And then the last thing, it's more on the team and personal level. You want to increase the visibility of the model that you build and you own to make sure that everyone else also recognizes the impact that you drive in the organization via the machine learning model in production. So now let's start with the first part, which is performance monitoring. It's a crucial step in the workflow. And why is that? First, business impact is whatever KPI we're kind of tracking, right? So we might track increasing sales, reducing churn, increasing product quality, reducing machine downtime, whatever is that your model is doing. There is some kind of business KPI. And then this KPI tends to be slightly disconnected for the actual predictions because there needs to be multiple additional steps that need to happen from the prediction to the actual business impact. And so this is something that we cannot simply track and say it's all because of model performance. There will be some other potential issues at play on people at play. So what we normally do is we're going to track machine learning metrics such as F1 as a proxy for that business impact that we're driving with our machine learning model. And we need to know them. We need to know these machine learning metrics, right? As a proxy to measure our business impact and to know whether the model is doing a good job or not. However, when we make a prediction, generally speaking, we will not have target data right after we make the prediction, which is kind of obvious, but it actually has very far-reaching consequences because we cannot estimate, we cannot measure or stop model performance drop, or we cannot stop model failure before the targets arrive if we don't know what's going on. So what we're going to do is we're going to try to estimate those metrics without the target data anyway. And that's going to be the part when we do not only performance monitoring with realized performance, but we'll be also estimating the model performance without access to target data. And again, why the lack of targets is so important, lack of ground truth after we make the prediction is so important. Because if you look at kind of the timeline of a single prediction, first, the model will get the inputs, it's going to process the inputs, it's going to give some kind of prediction. Then after a while, there's going to be some additional business steps that happen in the meantime. There's going to be a business impact. And then only after we have the business impact, so let's say we try to predict the sales of a product, then only then the targets will arrive, because we will see how much we managed to sell. And if model fails, if there is a significant degradation in performance, that will also impact the bottom line. It will have a negative business impact. So ideally, we want to catch model failure before there is significant model business impact, which means it's always before the targets arrived. So we never have the targets before it is too late, before the business has been negatively impacted. But we can solve it with performance estimation without access to ground truth. So how do we actually decide what to do? Again, it's about availability of targets. If targets are available, because maybe we waited and we were looking at past performance, or we're working in one of these few edge cases when targets are available almost immediately after making the prediction, then we can just calculate the performance. And what you see here is like a small snapshot from NanoML, where you will see the blue line here is realized performance, so the performance we actually observed in production. However, before we get the targets, what we'll have to do is estimate performance. And for that, we develop 3 models right now, 3 methods, 3 algorithms, one for regression called direct loss estimation, and one for classification, 2 for classification now. One is called PAPE, which is probabilistic adaptive performance estimation. Another one is CVPE, which is in our open source, where you can see that the performance estimation, I think here you see PAPE, which is a bit more advanced algorithm than CVPE, is able to estimate model performance before the targets arrive really, really well. And of course, this is one of the places where it works very well, but it generally can estimate performance without access to ground truth quite well immediately after we make the prediction. So we're able always to realize that the model is failing. Now, how is it possible to actually estimate model performance without ground truth? At the first glance, you could say that since we use all the available information in model inputs to predict the targets, if there was some way to predict the loss of the model or predict the quality of the predictions, we could just use that information to improve the model predictions instead. But funnily enough, this is actually not the case. This is something that, like, basically I also used to believe, everyone used to believe. Turns out that these are 2 separate tasks, and they're actually quite orthogonal in nature. To give you a bit of an intuition of how it's possible to actually estimate performance, imagine that we have the simplest possible machine learning model, where we have one feature X, which is a continuous feature, and we're building a regression model that will try to predict value Y. And we build the best fit line, which is just a straight line. It is bias optimal classifier. It's as good as possible, extracts all relevant information from the data. However, and we also see that there is one other pattern. And this pattern is that here at the low values of X, and the dispersion across the Y-axis is higher. The data is more noisy. And as we increase the value of X, the dispersion of data decreases. So intuitively, we can think that if the value of X, let's say between 0 and 2, we expect the model to have higher loss on average than if we have value of X between 8 and 10. And that means that we can actually somehow quantify this information about the dispersion in the data to estimate the model performance based on where the data distribution currently is in the model input space. And just to kind of verify this intuition, if I calculate the rolling mean error, I think this is absolute error of predictions, from 0 to 10, you see that indeed the error decreases linearly because there is a linear change in noise level from 0 to 10 with a bit of noise there as well. So we're not going to get absolutely perfect performance estimation, but it's pretty damn good. And now we have this intuition. How can we apply it both to regression as here and classification settings for models deployed to production? So to continue building that intuition, now let's switch to classification for a second. And imagine that we have a model where most of the data points are expected to have very low loss because the level of noise around those points is very low. We can predict the targets very well based on the model inputs. And there's, of course, a bit of spread, a bit of noise. And you also have points, like the point here, which is basically almost on the class boundary, where it's almost impossible to predict whether a model is going to belong to positive or to negative class. And now, if we deploy our model to production and the model undergoes covariance shift, so change in the model input distribution, we might actually see that the expected performance of the model has changed significantly. In our case, in most cases, it's going to drop significantly because the data distribution has shifted to a region where there is less information in the model inputs about the targets. For example, here right in the middle, where the model is just predicting a random value because there is no information in the data. And if that happens, we would expect the model performance to drop significantly. And we developed algorithms to actually quantify that change. Today, we're going to focus more on the actual flow and how to monitor your models, but we have open documentation and open science, and there's also an upcoming paper about the algorithm, so you'll be able to delve deeper if you want. Now, in terms of the algorithms, I want to explain just one more thing about DLE. The algorithm is actually quite simple, and here's how we can actually quantify or estimate the loss for every single data point for which we make the prediction. And it goes as follows. First, we calculate the loss metric on the reference data. Reference data is the data for which we know model performs very well. It is generally going to be the test set, and because by definition, model has to perform well on test set to be put in production. That was not the case, we would still be developing model because the model wouldn't be good enough to actually be put in production. So if the model is in production, then test set is a good reference data set that we can calculate the loss metrics. We always have the target data there. Then we're going to train a model to estimate this loss metric, let's say squared error, using the model inputs, the features, and also the predictions of our monitored model as a feature. We're going to train that model to predict the loss metric. And if there's any kind of relationship between the estimated loss or expected loss, so the dispersion of the data and where the model is in the model input space, which it almost always is, we can actually directly estimate the error on the monitored data, the loss of the monitored data for every single data point. And then if we aggregate those predictions, we are able to give a very high confidence inference or high confidence predictions or estimations about the level of performance of a regression model. Now, in terms of what metrics we can actually estimate, for regression, it's any metric that can be defined at an instance level. So it's root mean squared error, mean absolute error, mean logarithmic error, percentage error, basically any kind of errors that is normally used. So any kind of regression metric. For classification, we can, again, basically estimate any normal metric that's used in production, so confusion matrix itself, both for binary classification and for multi-class classification. We can also estimate precision, recall, accuracy, specificity, F1, any metric that is based on the confusion matrix itself. Then we can also estimate ROC AUC and average precision, which are also based on confusion metrics, but they are more combinatorial metrics when we're not sticking to one threshold, but we're kind of iterating over all possible thresholds. We can also estimate those. And then lastly, we can potentially estimate business value if business value of the model can be expressed in terms of how much money or value we're bringing for every positive for every true positive, false positive, true negative and false negative, etc. So if we can quantify that for every positive prediction we make, we're making, let's say, 10 euros, then we can also directly estimate the business value the model is bringing. And this is really a great way to communicate with business stakeholders that this quarter, this model is going to bring, let's say, 2 million euros. So it should really be monitored. Now, if we actually notice that there is a drop in performance, there is a performance issue, significant performance degradation, we're going to go to the second step, which is the automated root cause analysis. And in that automated root cause analysis, we'll enter kind of a mini flow itself, where we're going to start with running drift detection and data quality monitoring, which is normally something that already happens in the background, but only when you enter root cause analysis is the time to really look at it and go deeper. You can keep track of those, and there is a very significant change makes sense to also be alerted, but it doesn't make sense to spend time looking into all potential data drift that can happen. Because if you have a model with, let's say, 200 features, of course, there's going to be data drift. It's going to be significant data drift, and it will most likely not impact model performance. Then, once we have all those metrics, we're going to correlate them with model performance, and this again happens automatically in the background. So you'll be able to see which features drift and which groups of features and which data quality metrics drift together or change together with performance. And then there's only one kind of manual step that the user still needs to do, user being, of course, a data scientist that owns the model, which is using the domain knowledge that you have to determine what is the actual root cause based on the data drift and data quality signals. And then you're going to, generally speaking, arrive at three main reasons for model performance drop. The first one is covariance shift. Covariance shift is a change in the joint model input distribution. So if you look at any kind of changes in a single feature or correlation between features or any kind of even more complex structural change in how the model input distribution looks like, this is covariance shift. Then the second part is concept drift. Concept drift is the change in the relationship between the target and the model inputs. So this is something where basically we try to predict the target based on model inputs. This is the concept that the model is actually learning. So if that changes, again, that's one of the main reasons, I would say second main reason for drop in model performance. And we're going to figure out how to address each of those later on. And then the third one is data quality, which is just increasing incorrect or incomplete model inputs. So it's going to be increasing nonce, maybe some weird outliers when there's additional zero where it shouldn't be, categories that were not previously seen, all that kind of stuff. So data quality is also like a separate specific issue. It's going to kind of manifest itself both as data quality signals and quite often also as covariance shift signals. So we'll have to do a bit of more snooping around to figure out whether it's data quality or actual covariance shift. Now, in terms of the kind of toolset and the algorithms we have at our disposal for each of these groups, I'm going to go quickly over everything. We have quite a lot of tools right now available, so definitely we don't have time to go deeper into anything here. But just to give you a quick overview, for covariance shift detection, we can use univariate drift detection methods, where we have categorical methods, both distance and statistical based. Distance bands would be, for example, Jensen-Shannon distance. For statistical, we have KS test, chi-square, etc. And then we have continuous methods again. In terms of statistical methods for categorical features, we have chi-squared. For continuous, we have KS test, and then we have like a slew, I think 4 or 5 different distance metrics where you can compare the distance between one distribution and the other. And it gives you a very nice interpretable way of finding what features are drifting. However, this is something that has extremely high false positive rate. Features will be drifting all the time, so you should only look at it kind of as a last step in your process. Then we have the multivariate drift detection, when we can detect the structural changes in the data distribution. So if certain correlations change or more nonlinear relationship changes happen in the model input distribution, then we're going to be able to measure those with data reconstruction error and with the domain classifier. In terms of concept drift, we developed a new proprietary algorithm called reverse concept drift, when we can estimate the impact of concept drift on any of the metrics and also the magnitude of concept drift itself. In terms of data quality, we have a pretty basic standard set of unseen data detection for any kind of categorical data, and of course, measuring the number of missing values. Now I have like a quick flowchart, which is should help you conduct root cause analysis. So first, we're going to ask, are targets available? If yes, we can actually measure concept drift, and then we should absolutely do it with reverse concept drift. If we observe that there is concept drift, then we know that's one of the causes. Then after we do that, if targets are available, if they are not, we're going to go to the second point, and we're going to go to the second point anyway, and we're going to run multivariate data drift detection on all the features. If we detect that there is significant drift, we go to univariate drift detection for each of the features. And then if you actually see that there is drift signals there, then you can look at univariate drift and you say this specific feature is drifting. It's one of the causes. Then for all the features that are not drifting, we can, it's not something that's absolutely necessary, but we can, and ideally we should, run multivariate drift again for not drifting features. So the features that are separately not drifting. And that will help us uncover structural data changes. So not just drifts in particular features, but it might be that two specific features actually don't drift, but the correlation between those features changes, and the correlation between those features is actually the main kind of driver of information. Maybe you don't care about one feature in isolation and the other feature in isolation, but you care about the ratio between those features or anything like that. So if that changes, we have data structure change, and that is yet another potential kind of family of root causes. And then we're going to go up and we're going to look at data quality metrics, unseen data detection and missing data detection. And one of those happens for each of the features separately, of course. Then we know that data quality is one of the issues. And this kind of concludes a high-level description of the root cause analysis flow. Now, once we have this one of the four kind of main causes, we can go to issue resolution and see for each of the causes, what should we do to resolve the problem? And here, it's actually surprisingly simple. If we have covariate shift, so either change in the data structure or specific univariate features are drifting, or maybe both at the same time, which is actually what's going to happen most of the time, then we need to adjust the prediction thresholds. It's important to note that simple model retraining is very unlikely, almost guaranteed to not fully solve the issue or not even solve the issue partially, because if the data drifts to regions that are just very hard to predict on, let's say close to class boundary, then no amount of retraining will fix the model. The data is just now harder to predict on, and we have to live with that. And one of the best ways to still protect business impact is if you care more about, let's say, reducing false positives, or you need to keep false positives at a constant level, then you can change the prediction threshold to ensure that your false positive ratio is constant. Even before the model is acted upon, the predictions are acted upon, and before any business impact. So this is something that you can do immediately after the predictions are made. You can adjust the prediction thresholds and you will know basically what to do with it. You can also adjust other downstream business processes, but prediction threshold is something that generally data scientists have full control over, and they can just change it to make sure that the most important metrics stay in line. Then second part is concept drift. If we experience change in the concept that the model has learned, then we should just retrain the model. And nice thing about reverse concept drift, so our concept drift detection algorithm, it's actually, this is the strongest signal to retrain your model, because it might be that the data actually moves to a region where model predictions, it's easier to predict the target, but there is still concept drift. And if that happens, it might be that the model performance does not drop or doesn't drop significantly, but retraining your model would actually help you improve the model quality further. And you can do that by running concept drift detection, knowing that there is concept drift. If there is significant concept drift, you retrain your model and you will almost certainly improve the quality of your predictions. And then the last thing is data quality. Then should generally take it upstream, talk with data engineering, maybe data collection, and make sure, maybe with data vendors, make sure that the data quality issues are fixed upstream. That is almost it. We're gonna almost move to the second part, but before that, a couple of key takeaways. First, there is a three-step monitoring flow with performance monitoring, root cause analysis, and issue resolution, and it ensures continued performance of your models and continued business impact of your models. And then performance monitoring and estimation are crucial and cannot be replaced with just data-driven detection, because data-driven detection might not show anything, or it might show, it's actually quite likely to show a lot of false positives. We want to quantify the impact of covariate shift on model performance, and we can do that with performance estimation. Then third thing is data-driven detection is very useful, but it is mainly a root cause analysis tool where it really shines and it really kind of takes the central spotlight. And then the last thing is retraining will not always fix your problems, so you still need monitoring even if you retrain on a schedule or retrain very often, because if you retrain, for example, with data issues, your model quality might actually decrease and your prediction quality will drop even further. And retraining with pure covariate shift is probably going to be just a waste of time and money. That is really it in terms of kind of the presentation part of this webinar. And now it's time for William to take the stage and show how it actually works with a real-world data set.
All right, thank you, Wojtek. In this part, I will explain a little bit how these three components of the monitoring workflow, performance monitoring, root cause analysis, and issue resolution, come together inside of the NaniML model monitoring platform. Quickly going to show how you can get NaniML. We're available on the Azure Marketplace as a managed application. So that means that the NaniML application gets deployed in your Azure environment and that there's no data leaving your cloud. So all the processing happens on your end. And it's the same for AWS, where we're also available on the cloud marketplace. And there we deploy as a Helm chart, which basically kind of follows the same paradigm as a managed application, except this time you will need to spin up your own Kubernetes cluster and then put the Helm chart on top of there. And if you're on GCP, then we will ship the Helm chart directly to you. And after doing that setup, which takes around 30 to 60 minutes, there's a 1 month free trial. You will get the model NaniML up and running, and you will get an overview in the model monitoring hub. And as you can see here, I already added lots of models. There's like 10 models running in production, and we already have some insights for them. But before I'm going to be analyzing this together with you and explain our monitoring workflow, I'll first going to add some more data and actual data sets. And for that, we need to import the NaniML Cloud SDK, which is basically a Python package that will allow us to send data to NaniML and to configure our machine learning models for monitoring. What we do need to do first is to connect to the NaniML application. And then there's 3 types of monitoring that we can do. One is the retroactive monitoring, where we're answering the question, how has this machine learning model been performing for the past month, for the past quarter? And then we also have continuous monitoring, where we're answering the question, how is this model performing right now? And then when the target data becomes available, we can also measure the real performance. So that's monitoring when the delayed ground truth arrives. And the first thing we have to do is to load some data. And this is a Kaggle data set. It's called hotel booking. And every line is a customer for which we have some information about their holiday or their booking. And then we're going to predict whether this customer will cancel their booking in the coming months. And this is the reference data set. And the ideal candidate for the reference data set is the test set, because that data is kind of an ideal period where we know that the model is behaving as expected, and where we are going to leverage that information to calibrate and fit the monitoring algorithms for performance estimation, but also to set a baseline performance thresholds and to extract the baseline distributions for monitoring. And then we have the analysis data set, which is basically the production data. That's all the predictions that the model is being making after it's being deployed. And here we have the same kind of structure. Every line is a customer, and we will predict whether they will cancel their booking in the next 3 months. And in this specific setup right here, right now, we don't have the target data yet because it's 3 months delayed. And then there is the first step that we need to do is to provide NaniML with some type of mapping and explain, okay, this is the schema of this data set. That means this column is the customer ID, this column contains the predictions, and this column contains the target. We have to say what type of machine learning model problem it is. Is it binary classification, regression, or multi-class classification? And then we can create a model and add it to NaniML. And for that, we need to specify a name, provide the schema along, and say what the granularity of the monitoring analysis is going to be. Do we want our performance metrics on a weekly, a daily, or a yearly basis? And then we also pick our main performance metric, which in this case is just going to be plain old accuracy. And then I can go back to this application and refresh it. And then I will see that there's a new model right now for which we're crunching numbers. And we see that NaniML is almost halfway through crunching those numbers. And while we're waiting for that, I can quickly explain what we see here in this main dashboard. So as Wojtek explained, we have this performance first monitoring workflow. And that means that we will focus on this column mainly, which is the main performance metric. And in lots of use cases here in production, we see that the realized performance is missing for most of those use cases And that is because for those use cases, the target data has not been realized yet. So we cannot actually measure the real performance. And that's where our algorithms come in, because we've developed algorithms that can quantify the expected performance in production while we're waiting for the ground truth. And that is also the main value proposition of NanoML, that even though the target data is not available, that we can create some type of view on how the machine learning model is behaving in production right now. And we can see here that all of these models are actually behaving as expected, except this one where we see a red estimated performance. So for this model, we could potentially already start the root cause analysis and delve in deeper and try to figure out what is going wrong with the model. And it's only actually when there is an issue with this expected performance or with the realized performance that we're gonna start the root cause analysis, for which we will be using these tools: concept shift detection, covariance shift detection, and data quality issue detection. And one of the nice properties of having these algorithms that can estimate model performance and quantify the impact of covariance shift on performance is that in this case, we don't have to go and investigate these alerts here. These red dots are basically saying that there's covariance shift happening, but it's covariance shift that's happening that is not impacting the model performance. And this might be because there is strengths or some seasonality, or it's unimportant features that drift, or just statistical tests that are very sensitive and that throw an alert that the distribution has changed. Or there might be drift in the input space to regions where the model is fairly certain. Basically just an umbrella term for all changes that are actually not impacting the model performance. Like what Wojtek said, false alerts. And in that case, we don't want to actually go and investigate this much further, because we know that the model is being able to deal with these changes in the correct way. And that is an extra benefit to being able to estimate model performance in production. And right now we can go and delve deeper in this data set that I just added for the hotel booking. And we can see here that we have the performance on the reference data set or on the test set, the real performance. But then in production, we don't have a view on performance yet, because the targets have not arrived yet or have not been sent to NanoML. So in that case, we will be using this algorithm to estimate model performance, and we can get the expected model performance on the test set, and then also here the expected model performance in production. And as we can see, the expected performance falls between these two performance thresholds that are derived from the test set, and we are considering that there is no performance issue in this 2 months because it has not dropped below these thresholds. So right now, we wouldn't receive an automated alert. Everything is working as expected, and there is no need for us to go and trigger a root cause analysis workflow. I'm going to add a little bit more data, and that is also going to be in the same way that we would do continuous monitoring with NanoML, which is basically we fetch which model that we want to send new predictions to, or send the new predictions of. And then we just fetch the new predictions, and we can either send them as batches or single predictions if the model is deployed behind an API. And then we have the ability to trigger a monitoring run based on the business needs or the granularity of the monitoring analysis. For instance, if we're monitoring performance daily, then we're not going to trigger a monitoring run after every single observation that's being sent to NanoML, because one observation might probably not actually impact the daily performance. So maybe we want to send this trigger this monitoring run rather at the end of the day. And that is the main way to do continuous monitoring, and we can just pipe the same predictions that the model is making to NanoML, and then we can have a view on the real-time performance. Right now we can see how far NanoML is with running, but it already finished with executing the last batch of data. And right now we can see that here in this month, there is a drop in performance. So right now we're going to start our root cause analysis workflow to figure out what exactly went wrong during this month, and then also how we can potentially resolve the issues. So we're really obsessed about model performance, but that doesn't mean that we don't or cannot get any other alerts. Here you can create other cards as well. For instance, features that you know that from a business perspective, when they change, that you also do want to get alerted. But that is based on the business context in which the model is operating. So right now we've established that there is a performance issue, and then we can go and delve deeper and find out what actually went wrong by triggering the root cause analysis workflow. And the first thing that we can have a look at is other performance metrics, because we were just looking at accuracy, but we can, for instance, also look at business value. And inside of the model settings, we can define something that is called a cost-benefit matrix, where we can basically specify how much money we will make if we make a correct prediction, and how much money we will lose in terms of opportunity cost when we make a false positive or a false negative prediction. And then we can map this cost-benefit matrix to our expected performance metric, and we can basically express this metric in monetary value. And this is very interesting to communicate this as well to other stakeholders, because we go from the machine learning realm more to the business realm, and everybody can understand when the numbers are going down. And as we can see here, that even in the month prior, that would already, from the business perspective, be considered an issue. Then the first thing that we would do in terms of data drift detection is concept shift detection, but because there is no target data yet, these cannot be calculated yet. So we're going to do covariate shift detection instead for the time being. And the first thing to have a look at is to see how the data structure changed across the input space. And for that, we have multivariate data drift detection, where we're going to look at the underlying changes based on PCA. And we can see here that in this last month, there was indeed an issue from a multivariate data drift perspective. And then we can delve deeper by using either some distance measure or some statistical measures to do the univariate data drift. And for instance, I'm going to select Wasserstein distance, but this is rather a big data set and there's lots of features inside of it. So what we can do as part of this root cause analysis is to actually only show those features that have an alert when there is an issue with the main performance metric. And then we can also switch to distributions to better understand how these features are actually changing and what might have caused them to change. But since we don't know these features very well and we don't necessarily understand their distributions deeply, we might want to have a look at the summary statistics of these distributions, where we can, for instance, look at the average. And then we can see here that the average lead time in production has gone down. So bookings are being made faster. Also, the repeated guests have gone up. So bookings are made by people that have made bookings before. And then when it comes to the previous cancellations, the average has also gone up. And it's those two things, those three things, that in this case will have led to the model deteriorating and actually also outputting a higher probability for bookings to get canceled. And this type of root cause analysis typically gets done by the person who built the machine learning model, or at least the person that understands the data and also the context in which this machine learning model is operating. And then you can put 2 and 2 together and understand the underlying issues. So this root cause analysis is partially automated, but it still requires some data science intuition to piece the pieces together. Then we can also have a quick look at the data quality issues, where we have the same property where we can just look at those alerts that happened at the same time when there was a performance issue. And we see indeed that the target data is still missing in this case, which makes sense. But we can also see that for country, there is unseen values. And that means that in production, there is new countries that weren't seen or that weren't part of the test set from which new bookings are being made. Not a lot, very few countries actually, but this might be something to look into, not necessarily from a performance perspective, because it's very few, but more from a perspective that the model might not necessarily generalize well to these new type of unseen data. And that's the first round of root cause analysis that we've done. And then we can add a little bit more data. 3 months more of production data. And we can also add the target data. So in this case, we're just gonna send the actual customer IDs and then the outcome of those customers, whether they ended up canceling their booking after 3 months or not. then we will send them to NanyML, and then NanyML is gonna connect them to the right predictions, and that way we will get a view on the real performance. And I'm going to refresh, and this is probably going to take a second to complete. In the meantime, actually, it already calculated the real performance. It is still recalculating the estimated performance. And right now we can see here actually that we do get a view on the realized performance in production. So in this case, we know for a fact that indeed this month the model performance deteriorated. And maybe to quickly show what that actually means is that right now we can compare the expected performance with the actual realized performance, and we can see how good we were at estimating it. And the biggest advantage here is that we would already know 3 months prior to actually getting the realized performance. And that is very, very powerful, because that means that at the moment that we make the predictions, we can already get an idea of how they're going to perform. And if the performance deteriorates, we can already take some defensive or some remediation actions to prevent the bad predictions from having a downstream negative business impact. And this also means that as a data scientist, you will always be the first to know when the model deteriorates. If you solely rely on the realized performance, and you will have to wait 3 months to get a view on how the model performed in that window of time, it might be that maybe the people that consume your predictions or the business processes might already have failed or came back to you and knocked on your door as a data scientist and said, hey, I think there's something wrong with the predictions. But with expected performance, you would already know before they actually have a negative downstream impact, and then you can potentially resolve these. So that is a very, very big added advantage of quantifying the impact of covariate shift on performance, because then you will always get a view on how your model is expected to perform. And you do not become dependent on the availability of the ground truth, and you can take actions faster. And since right now we also have some target data available, what we can do is we can, for instance, go and look at concept shifts. And concept shift is expressed as an accuracy delta. So it's answering the question, what is the impact of potential concept shift on the performance? And here we can see that during the testing phase, the concept is fairly stable. And in production as well, it kind of follows the same stability. So we can already rule out that one of the root causes for concept shift, for the model deterioration, is concept shift. And that means, like Wojtek had explained earlier, that retraining the model might not necessarily gonna make the model performance better or resolve this specific issue, because we've just established with this algorithm that the same patterns that were valid during testing are still valid during production. And it's by piecing these types of insights together that we can then pick our appropriate remediation action. And sometimes, for instance, when there is concept shift, what's possible is to configure, for instance, webhooks, where you can then just trigger an automated retraining pipeline with some logic here inside that would then solve the issue by retraining the machine learning model. But unfortunately, not all issues today or all root causes can be solved automatically. But pure concept drift would be one of them. And that concludes a little bit the entire workflow of model monitoring inside of NanyML, where we start with performance estimation, where we do root cause analysis and get to the bottom of what the actual underlying root causes are for the model to deteriorate, and then how we can go into issue resolution, and where we can send from NanyML with webhooks, trigger automated other systems to resolve the issue, or a data scientist themselves look at it and piece it together. And that concludes the practical part